About the homework session. Unless I have time at the end of the lecture, which is doubtful, I'll be there at the beginning of the homework session to talk over some of the answers to the first exercises, because some of them are quite tricky, and I noticed that some of the people that were working on them, they didn't come out quite right. So I thought it would be worthwhile to actually have a short discussion about one or two of those exercises, which were tricky. Okay. Okay, so that would be at 2 o'clock. So what I wanted to talk about today is computation interpretations, or you can also give it the title Curry-Howard isomorphism. And I'm going to depart a little bit from my original schedule of the subtopics underneath the lecture, because as I was writing things down on the board yesterday about the different logics and how they correspond to different computational phenomena, I thought it was important to give you some examples of that to make this a little more concrete. Okay. So one example I will definitely give you in this lecture, which is capturing a generic notion of effect. So we'll take a look at what's called in functional programming monads from the logical point of view and see what we can reconstruct and how the computation interpretation of monads come out of logical considerations. If I have time at the end of the lecture, which at the moment seems doubtful to me, I might talk about quote and eval as well. So, languages like Lisp or Scheme, they have this notion that you can quote an expression, you can evaluate while the program is running, and we don't traditionally have this in functional languages that are statically typed, like Haskell or ML. And the question is, why not? And so I'll try to give you a foundation that would explain how you could introduce it into a functional language that is statically typed if you wanted to, and how it would work in that case. Okay. All right. So, but first we need a review, okay, and also fix the notation a little bit more. So we had this two-dimensional notation for proofs, which is traditional in proof theory, right, where you have assumptions at the top and the thing you're trying to prove at the bottom. And as you're doing your proof, you fill it in both directions. If you've done the exercises, you know what I'm talking about, right? That's nice from an intuitive point of view. But when you actually want to write things down, it gets awkward, which you also probably noticed. Okay. So the way we're going to write things is like this. Okay. So we have a context gamma, we have a turnstile, and then we have m colon a. And if I want to be very explicit about it, I'm just doing it once. When I write this, I actually mean this is a proof that A is true. And this will play an important role later on. I'll omit the true because m colon A just stands for M is a proof of A, therefore A should be true. If you need other judgments about propositions, we'll have to revisit the notation. So what is gamma here? Well, gamma is just, if I want to be, it's either empty or it's gamma with a declaration of the variable, has type A. And there's a very important restriction, which we already noticed when we were doing our two-dimensional notation, that they're all variables that are distinct. So that we don't get confused as the variable is being used, which variable we're actually referring to, of type A or of type B. Okay, so in the context, all the variables are different from each other. Okay. So with that notation in mind, we can go back and just rewrite what we had before. Okay. So we had conjunction introduction, which is something like, if I write it with a context, it would be this. If I have m colon A, and I have gamma turnstile n colon B, then the pair m comma n is a proof of A and B. Okay, this big enough for everybody to see? Okay. All right, so this was the introduction rule, and we viewed this as defining the meaning of conjunction, okay? And from a programming language point of view, it's a product or a pair of two proofs. And from that, we derived and justified the two elimination rules. If in gamma m has type A and B, then in gamma, first of m has type A, and in gamma m colon A and B, then in gamma second of m S type B, and that's the second elimination rule. Okay. And then we had a witness to the local reduction. Okay. A witness to the local soundness. If we introduce and then eliminate the connective, then we can back the original. We can reduce that to a simpler proof, and that was if we take first off the pair m comma n, then that locally reduces to m, and the second part of it was if you have second of the pair mn, then that reduces to n. And these rules are called, they're projection rules, but they're also called collectively beta rules. And these are computational, because if you have a pair, there's a computation that extracts a component. Okay. And then we had a second thing, which was to make sure that the elimination rules were not too weak. Okay, so that we can, if we have an arbitrary proof of A and B, we can apply the elimination rule in such a way that from the pieces we get, we can reintroduce the connective. And that was the a local expansion that said if I have a term M of type A and B, then I can expand that into a pair, first of M, second of M. Okay. Okay, and so these rules are called beta-like rules, and these are eta-like rules. Okay. Okay, then in order to explain implication, okay, we needed a new idea, and the new idea was substitution. So I'll put that. Okay, maybe I'll put it over here so I can keep it up a little bit longer. Okay. So the introduction rule, we'll come to the substitution in a second. But let me first write down the introduction rule. Okay, to prove A implies B, okay, I assume X colon A and prove B, okay? And this assumption has a scope, namely the proof above here, okay? So it's not visible outside. And it's very easy to see that if you write it in this kind of localized notation where the assumptions are listed on the left, okay? Which was not very easy to see in this two-dimensional notation. It's easier to see here. So if M is a proof of B, okay, then this is actually a function lambda x dot m, okay, is a proof of A implies B. So another way to think about this, a proof of an implication A to B is a function which, if you give it a proof of A, it gives you back a proof of B. So that's the ordinary intuitionistic interpretation of implication. And then the corresponding elimination rule is if I have M of A implies B, and I have N of A, then I can apply that function to N and get a proof of B. Okay, so that corresponds to applying this function, which if you give it a proof of A gives you one of B, to a proof of A, and you get back a proof of B. And we just write that by juxtaposing M applied to N. Okay. So now the local reduction says if I introduce the connective and then eliminate it, okay, what does it look like? Well, if I introduce it, it's going to be lambda x dot m. And then I eliminate it, so I apply now the elimination rule here to some n. I must be able to reduce that. And that I reduce that by substitution. Okay, and so this notion of substitution, we didn't really define in full detail, okay? But it's what Bob called plugging in, that you plug in n for x and m. There are some things you have to be careful of when you do this kind of plugging in, okay, if you were familiar with variable capture and so on. I don't want to get into too much detail about that. But one thing to notice is that it's defined based on the structure of m. Okay, so you look at the structure of m. If m is a variable x, you just return n. If it's an application, you push it into both sides and so on, right? You traverse the structure of M in order to do the substitution. Okay. Now it's important that in this formulation, this is kind of a primitive operation in the sense that this is not a term, okay, in our language of terms, but it's something that's defined that you work out to get another term out. Okay. And this is, of course, a computation rule. It tells you how to apply a function to an argument, and the way you do it is by substitution. Okay. Never mind that that's not really how it's implemented, but that's the definition of what it's supposed to mean. Okay. And then we have an eta-like rule. So this is a beta-like rule, which is computational. And then we have an eta-like rule, which gives you some kind of extensionality principle. Okay. Anybody remember what that is? How do I expand if I have something that's a function from A to B? Right. So I take lambda x, I take m applied to x, and that's an eta rule. Okay. And of course, these two should behave the same when you apply them to any argument, okay, because when you apply this to an argument, you get m applied to the argument n. If you do that, then by the computation rule, you get m applied to n. So these two things should be equal. And similarly here, these two things should also be equal. If you try to observe what they are, if you try to take the first component of m over here, okay, that should be the same as taking the first component of this over here, because what happens is you take first off this pair, but that's just first of m. So if you apply the first projection to this side, then you get the same thing as if you apply the first projection to this side. Okay. So in that sense, these eta conversions or eta expansions, as we've written them, are some kind of extensional equality on these terms, right? If you apply both sides to some argument, these two functions behave the same. If you project away from the term m with the first or second projection, the result will always be the same. So these give you some kind of equalities. And at some point, Bob may talk about how you treat these equalities. Are they definitional? Are they denotational? Or are they, what's the last one? Are they homotopy equivalences? Whatever. So he'll have to come up to some decision about that. Okay, it's not my problem. Okay. Okay. All right. So, but we actually should think a little bit more about the substitution, okay, because it'll play a very important role. So, so the substitution is kind of, in some sense, a computational engine here, okay, because these are all kind of small steps here, but this thing is a big step, okay. And also, as a side remark, we have said that this is a reduction, so we reduce this to that, and that's true from the point of view of computation. But it's actually not a reduction if you think about the size of the term. And the reason is because if the variable x occurs multiple times in m, which corresponds to using an assumption multiple times in a proof, then after you do the reduction, okay, this term here will be replicated in m. So the result of the reduction may actually be much bigger. Okay. Okay, so we should keep that in mind. Because eventually you want to prove some properties about the system, and then a certain thing, namely looking at the size of the terms, is a way that's close to us. Because as you do reduction, okay, the terms get bigger and bigger. Something else gets smaller. Okay. If you want to prove, for example, that any sequence of reductions terminates, can anybody guess what's actually getting smaller if it's not the term? The type, right? So we have to find some way of engineering that the type's getting smaller, because here we introduce A implies B, and then we eliminate it. Okay, we introduce it, then eliminate it. And so A implies B, that type is gone from the thing over here, right? Because we substitute a term of type A for a variable of type A in a term of type B, so the implication is gone. So we'll have to leverage that when we want to prove properties of this, which will be in the next lecture, not in today's. But the substitution operation, okay, if you want to write it out in this notation, has some property which is like this. So if you have gamma and you have a n colon A, and you have a gamma with an x of type A, and then you have an m of type B, okay. Okay, so I shouldn't write this line. Sorry. I've yet to find a good way to write this on the blackboard, but it's something like this. Then n for x in M is a proof of B. Okay. So what I'm just stating here, we can apply the substitution only in certain circumstances, namely when the type of the term that we're substituting is equal to the type of the variable that we assumed. Okay. That's completely natural here, because we only apply it in this context here to a term that's well-typed. If a term is well-typed, that means that the assumption will be x of type A, which has to match the type of n here. Okay. Now, this is not supposed to be an inference rule. Okay. Because if it were an inference rule, we would create a problem for us. Okay? The problem is the following. This thing down here will actually reduce to an actual term. Right? It's not actually a term in itself, but it will reduce to something else. If this was an inference rule, there would now be more than one way to type a given expression. One would be the rule for, say, implication, if the result of this was a lambda abstraction. And another thing would be use this rule. Okay, we want to avoid that. We don't want to pollute the rules. Okay, so this is what's called an admissible rule. So it's something that we know if we have a proof of this and we have a proof of that, then we get a proof of that. But in itself, it's not a rule. It's a property of the system. Okay, does that make sense? Okay, it's very important to distinguish between things that are property of the system and the things that are inference rules. And the reason is that eventually in the next lecture, probably not today, we'll do things like analyze the structure of proofs in detail and do induction over the structure of proofs. And then we won't account for this rule. We don't have to account for this rule because it's not a rule. Okay, it's just a property of the system. Okay, so if this is true and this is true, then this is true. Okay, so that's why we have to not actually take that into our system. Okay. All right. Everything okay so far? All right. Okay, so now I'm not going to do disjunction and falsehood today, but I want to introduce some new concepts. Okay. Okay, so a simple way of thinking about this, or actually there's many different ways, but I want to try to capture generically the notion of an effect. Okay. Now, effects can be many different things. It could be input and output. It could be some kind of communication. The thing which is often a useful guide is non-termination. Okay, so I might have recursive functions, okay, in my language, and I want to account for the possibility that a computation might not terminate. Okay, but so if I can't say something like this in the context gamma. If I have possibly non-terminating computation, let's call it E, okay, that's evidence for the fact that A is true. Okay, so it's incorrect to say that, because if I try to get out what this actually is, the value of it, okay, if I try to compute out the value of type A, it might never actually terminate. It might not give me an A. So it's actually not good enough as evidence for the truth of A. Okay, it doesn't count because it may not actually deliver me a real proof. It might compute something, but it might not give me a proof at the end. Okay. So I can't write that. What I need to do is I need to make up a new judgment. Okay, so the first time, actually we have one judgment and one judgment combinator so far. The judgment we have so far is truth, A is true, and the judgment combinator is a turnstile, hypothetical judgments, which you take judgments and build more complicated ones. Okay. So what I'd really like to write here, but I can't actually, okay, well, I can write it, but it'll be wrong, okay, is A is possible, okay. So that would mean that it might deliver me a value of type A. It might be a proof. I'm not sure, it might not be. Okay, that's what possibility could mean. Unfortunately, in modal logic, the notion of possibility is too weak for what I'm trying to do here. So, based on what's been done in logic, I'm going to call this A is lax. Okay. So think of it, you can think of it as possibility and won't be far off, okay? So lax is weaker than truth, right? So, in particular, we have a principle that says something like this. So now we have to, okay, so I should say that lax truth should be a derived notion, somehow from the notion of truth and by the inference rules that I give, okay? So the first thing I'm going to tell you, if A is true, then A is true in this lax sense, okay? Because this is a much stronger promise. This means I have really a proof, and this means I may have a proof, okay? So obviously this thing is stronger than that. So I have a rule, okay? Let me just call this lax. That allows me to do this, and then if I write in proof terms, it'll just be like this. If M is a proof of that, then M counts as evidence for A is true in the lax sense as well, okay? So I allow this as evidence as well, okay? So this is an honest-to-goodness proof, okay? But there might be other things which aren't really proofs, okay? All right. So the next thing I need to do is, let's see which way to proceed. Okay. This rule, by the way, if I think about it, okay, is not the kind of rule that we had before. Okay. So what we've had before are rules that introduce or decompose connectives. Right? Introduction rule introduces a connective, elimination rule eliminates it. This rule does not have this property, okay, because there's no connective involved. It's only a change of judgment. And so these are usually called, sometimes they're called structural rules. And sometimes they're called judgmental rules. Because they serve not to talk about the propositions, but how the judgments that you're working with are related to each other. Okay, so that's why I prefer to call them judgmental rule, because it's hard to see what kind of property of the structure here of the judgment that I'm making actually changes. Okay. Okay, so the next thing I'm going to think about is what kind of analog of a substitution principle I might have. Okay, so if you think about it at a high level, okay, you can think of this kind of like a way to introduce the lax judgment, kind of, right? If A is true, then A is lax. Okay. The question is, what do I do when I know that something is true in this lax sense? What can I do with that? Okay. And so I'm going to have something like this. If gamma A lax, okay, how can I use that? Okay. So it would be incorrect to just say, if A is lax, then A is true. Right? Obviously, it's supposed to be weaker, because let's say, if you think about it as a computation, it might not terminate. So I can't just say A is true. Okay, so what else could I extract from the knowledge? Okay. So what I'm going to do is the following. I'm going to say if I assume that A is true, okay, then I might conclude that okay, C. Okay, let's leave it as C for the moment. And this is one of these things that looks like the substitution principle. So I'm going to use these dashed lines. Then I'm allowed to conclude C. Okay. So the idea is okay, so this is some computation here which I can run. Okay. If it terminates, okay, then I get a value of type A, basically. Okay, I get evidence for the fact that A is true. So I'm going to allow to assume that I have that evidence. Okay. Then I'm allowed to do another computation. Okay. And that will have to be that. Okay. And at the end, I get some computation which may or may not terminate, which goes directly to C. Okay. And so if this is some computation E, then this is some computation F. And then this is some kind of a substitution, and the notation I made up for that is E for X in F, which is the computation of C. Okay. So this is not an inference rule, because this is an operation on proofs, on computations, if you will, these Fs. So you should think of it the same way as this rule over here. Okay. So I haven't defined that, and I'll put off defining that for a little while. Okay. Because I don't have any propositional connectors yet. This is also a judgmental rule, right? So this is one connection between truth and lax truth. It says if A is true, then A is lax. This says if A is lax, I'm allowed to assume that A is true, but only in the context of another computation, right? So why would it be wrong if I allowed this thing here to be true? Why would that be wrong? Excuse me? Right. Exactly. So if you think about the effect as being non-termination, this F could try to refer to X. Well, in order to have X, I need to carry out E, but E might not terminate. So this, if you say true here, that's an extremely strong promise. I will guarantee give you a C, okay, a proof of C. But you actually cannot, because this A may never deliver its A. may never deliver the proof of A. So therefore, we can compose two of these computations, the computation E and the computation F, okay? But we cannot compose a computation with a proof of truth and expect to get truth out. Okay, makes sense? Okay. So it really has to be C-lax. Okay. Okay, so if you have ground functional programming in language like Haskell, okay, just to give some preview of the determination, this corresponds in some way which will make precise to unit and this, or return, and this corresponds to bind. Okay. But if you forget about what these things are, if you forget about the proof terms, right, it's just a logical notion of lax truth. Okay. Okay, so now from this seed, we're going to grow some more things. Okay. This is always the way you usually think about a computational phenomenon is that you have to think about what judgment is involved. So in this case, some kind of a weak notion of truth, because you might have non-determination, say. And then you have to build from that sort of the logical connectors that you can actually embed in the programming language, make part of arrows, and so on. Okay. So this process is what we sometimes refer to as internalizing a judgment into the logic as a proposition. Okay. So what we're going to say is the following. Okay. So the new proposition is going to be circle A, and we want to know when that's true. Okay. So this is the I think often in the functional programming literature, this is written like an M for monad A. In the logical literature, it's written as circle A, which stands for, well, A is true in this lax sense. Okay. And when should this be true? Okay, so I'm going to fill in the rest. So what is the introduction rule for that? Notice that this is now a proposition, right? A or lax was a judgment about propositions. Can anybody guess what that is? What's the introduction rule? When is circle A true? If A is true, certainly that's valid, but that's too strong. Okay, requires too much. We only require that A is lax, right? Okay? Okay, and this is in some context. We have an E in computation, that E is lax. And so we have to have some way of embedding computations in terms. And so I'm just going to write it like this. I'm going to write braces around E. Okay. Fortunately, we don't need to do that in the functional language because there's a different way then to embed it eventually into the functional language, so we don't really, this notation we only use in the proof theory. Okay, so that's one. That's the introduction rule for circle. And the elimination rule has to be something like, if we know circle A is true, okay, how do we actually use that knowledge? Any suggestions? So we have to look what's on the board here in order to come to, right? Any ideas? Yeah, back there.
Cut operation above, where
The substitution, yeah. Mm-hmm.
where we can give circle B is true if we assume A is true, proof B lax.
Right. Okay. And you'll see when we check whether this rule is locally sound, is that it just reduces essentially to the substitution principle, which is why we construct it this way. Okay, so let's fill in some things. So this is going to be some term M. Okay. This is going to be some computation, let's call it F. Okay, because evidence for C lax is some computation. Okay. And so here we have some new construct. Let's call it let x equals M in F. Okay. Okay. And that's the elimination rule. for the monadic constructor for propositions. Okay. So now we need to check that this thing is locally sound and complete. And that should tell us something about how we compute with these things, right? Because computation arises from checking that these things are locally sound or complete. How does computation arise? Sound, right? The local completeness check is some kind of eta expansion, which is an equality, right? And computation should arise from checking that it's sound. Okay, so how does it work? We have to check that we introduce and eliminate it. Okay, so if we have something like this, gamma E colon A lax, then gamma brace E colon circle A true, and then we eliminate again, so gamma X colon A true, we prove F colon C lax. Okay, so that's circle I, circle E. Then in gamma we have let X equals E. In F is a proof of C lax. Okay? And so now, how do we reduce that? How do we compute that result? Anybody see how to do that? Yeah? Right. Exactly. So we want to take this E and we want to substitute it for X here. Okay? Now we can't exactly substitute it according to the usual notion, but we have that principle up there that we started with, right? That should always be true. So we can take that E and plug it in here, so we get something like, we get E for X in F should be evidence that C is lax, or computation that C is lax, and that should be in context gamma. And why is this well typed? Well, we have the two assumptions. They match exactly the premises of the rule up there. Right? Okay. Okay, so I think that shows that it should be locally sound, assuming that we can define this operation properly. Okay. What do we need for local completeness? So what do we need for local completeness? The elimination rule is strong enough. So we need to take an arbitrary proof of circle A. So M is a proof of circle A. Okay. And we need to be able to expand it into a proof in which we apply the elimination so that we can reintroduce circle A from the pieces. Okay, so how do we do that? Okay, the elimination rule. Okay, probably would help if I left that there. Okay. Let bracket X equals M. Okay. So that's actually not quite right, okay, because this is M is of type circle A. The conclusion of this actually has to be C lax. So it's not quite right. So how do we fix it? Exactly. So we have to move the brackets outside. Yes, because that, okay, by the introduction rule, that's a proof of circle A true, which is what we started with, right? M colon circle A. So that's of circle A if the thing underneath, which is the computation, let X equals M in X is A lax. This is circle A true. Okay. And when is this the case? Well, we have to show that m colon circle A. Well, that's what we have here. And what do we have to show in the second premise? We have to show that x is a term of type C lax, right? Actually, in this case, A lax. X colon A lax. And we're allowed to use the additional assumption x colon A, which is the same as saying x colon A true, right? So that's just pattern matching against this rule. So how do we go from x colon A true to x colon A lax? Right, we need that lax rule that says if something is true, then it's also lax. Right. So this comes from x colon A proves x colon A, and that's the hypothesis rule. Okay, and this is the lax rule. And this is the thing we started with. And let's put the gammas here to make this complete. Okay, so there we are. Okay, so what do we get out of that? So I think let's summarize that on terms. So the first rule says that if we have let braces x equals braces e in F, that reduces to e substituted for x in F. And the second thing, if we have m colon circle A, that expands to brace let x equals m in x. Okay, everybody with me so far? Okay, so that's where we are. Okay. So the rules are sound and complete. Okay. And so in some sense, the main issue now is the thing that we haven't done yet. We haven't defined this funky kind of substitution. Okay. E for x and F. And why is it funky? It's funky because the two things that we're substituting don't actually match up. Right. We have A lax over here and we have A true over here. So we can't just plug in that expression for the variable, okay? Because the two don't actually match. See, here we can, because here this is n is a term of type A true. The assumption is x A is true, so we can just plug it in, okay? But here we can't just plug it in, so we have to be a little bit more careful about defining that operation, okay? So let's try to do that here. So what are the possibilities that we have for E? What are the possibilities for the expressions E? Let's write that out. So in E, a computation E, what are the possibilities for it? So this is just, I think it's just all on the board. So one possibility is that it's just a term, right? That comes from this rule. Because a term counts as evidence, so a term is a kind of a trivial computation, okay? So one of the possibilities that it is actually a term m. And there's one other possibility, okay, which is that it's one of these let things, okay, which comes from here. So the other possibility is that it's let x equals e in some kind of E prime. Actually, I'm going to use F for that. So it's an E or an F, stands for computation. Okay, and the terms M, how has they changed? Terms M were everything we had before, okay? And there's just one new possibility, okay, which comes from the circle introduction rule. It could be one of these computations, okay? So it could be E. Okay, so that's the way our language of terms changes. Okay, so that helps us because now we can define this operation. Okay, so let's look at this rule. We account for the different possibilities for E. Okay, so what if E is an M? So what if we have E substituted, M substituted for X in this funny way in some kind of computation F? What do we do in that case? is just regular substitution, because in that case, this E, okay, is actually an M, which is A true. And now that matches up with our assumption that we made here that A is true, so we can just do an ordinary substitution. M for X in F. Okay, so the interesting case is if we have a let X equals E in E prime substituted for X in some computation F, right? So the parentheses here, we have to be careful about that, is like this. Because that's another, so if I had kept it like this, that's another kind of computation as one of these lets. Okay. So what should happen in that case? Okay. So what should happen in that case? Sorry. Did I make a mistake there? It should be let X equals M, right? Right. This should actually be a term M, right? Because that's what we have evidence for here. So I actually should have said M here and M here. Sorry about that. Okay. Okay, so what happens in that case? So in that case, we have to analyze the structure of this particular rule, okay, and see what we actually have to do in this case. So what we have to do is, if this is an elax and this is another one of these computations, then we just pull it out, and we have let bracket X, brace X equals M in the result of substituting E prime for X in F. Okay. Okay, so essentially what we do is, if you think about the computation, we do the computation M first, where we do the evaluation of M first, okay, and then we do the E prime for X and F. Okay. Something isn't right. Yeah. I think this X equals M was my... Okay. Yeah?
X equal N.
No, they're not supposed to be the same. There's something else is wrong here. Let me try to catch what the problem is. Okay. So this should be a Y. And this should be a Y here, right? Okay, it seems okay now, but does it seem okay to everyone?
I would expect that you would be finding it that the only term you are substituting in, so
Right.
so short of F instead of...
Right. So that's what changes here in this kind of substitution. Okay. When you compose computations, you do the left computation first and then the right computation. Okay. So therefore, we have to find it by induction of the structure of the E rather than the F. So the difference between this ordinary substitution, okay, where you go inductively on the structure of M, for composing computations which may have effect, you have to do the outermost, the leftmost computation first. So the substitution operation pulls out, so to speak, this part, leaves it behind, and then recurses on the left, and the right thing you're substituting does not change, okay, until you have reached a value that you're returning, in which case it turns back into ordinary substitution for a value. Okay. It actually enforces a sequencing that you may be used to if you've worked with a monad in a functional setting. Okay. So here it's accomplished by the notion of substitution, which is defined inductively on the left-hand side, okay, rather than the right-hand side. Yeah?
Why did you choose to have a true judgment for the M? Could we have M lax instead M A lax instead of A O A?
Okay, so that's the substitution principle. The elimination rule is defined how you eliminate a propositional constructor. Okay, So the introduction elimination rules are always concerned with truth. We don't change that notion. Okay. Okay. So the introduction rule tells you when circle A is true. The elimination rule tells you how you use the fact that circle A is true. Okay. So that's as before. Okay. Yep.
Is there a reason why both lax and circle A, lax of the judgment and circle A as a proposition? I mean, I'm not terribly familiar with this, but why do we do that?
Okay, so you can try to the monad directly without defining a new judgment, but you will find that the proof theory does not work out. Okay. So basically, there's not enough structure in the propositions themselves in order to give a good definition of it. Okay. So the original formulation, which comes actually from category theory, which the notion of the is defined equationally, and there's no separate judgment involved. But if you want to do it computationally, then I think this is probably the best way to do it. So Moji had a formulation of this which was directly on terms, but what happened is that there is a computation rule which actually has to just commute the term, which doesn't actually do any real reduction. Okay, it's a commuting conversion, and that's an artifact of the of his decision not to have a separate judgment of lax truth. Okay, if you have a separate judgment and then you internalize it as a proposition, then it works out well in this case. Yeah.
Elimination rule.
Yeah.
It's clear that this one works, but I wonder about a different one where C lax is replaced by C true in two places.
Over here?
Yeah.
Yeah, well, we already know that that can't be true, correct, because if you say C true, okay, that is definitely going to return a value of type C. But because this thing may not, in fact, return a value of type A, okay, you are not actually licensed to say that this will return a value of type C.
Certainly you're wrong to replace it just on the... Replace it also in the premise would be wrong?
C could be A itself, right? And then
So if this was A,
A.
it could be A true. That's but you can't actually be true. So if you want to fix that rule, the way you have to do is you have true here and circle C true here, and that's a problem because then the elimination rule is not what we call pure. It actually has to look inside this proposition, which is the thing that messes up the proof theory. Okay. Okay. So it definitely needs to be C lax. Okay. Okay, so let's see, where are we? Okay, so we want to do a little bit of computation with this, but let's do some warm-up exercises. Okay, maybe I can get rid of this now. Okay, so I want to now see some of the things which let's see. I want to work with properties of proof terms for a little bit. Okay, so before doing this for the lax truth and the monad, let's back up a second and let's do it for our original language, just for implication and conjunction. Okay, so I'm just backing up, and then we'll go into this. Let this sit there for a little bit. Oh, you have another question?
You said we introduced lax for coping with non-termination terms, but we don't have actually had opportunity that we introduce non-termination right now.
Right.
So I'm planning to introduce side effect later.
Okay, so that will be up to John. He comes and talks about how the monads are used in Haskell. Okay, so this is sort of the abstract notion. Okay, sort of and it covers kind of all different kinds of possible effects, not just non-termination. It's useful, I found, to think in terms of non-termination. So I could introduce a recursion construct and give you the typing with respect to lax truth and circle. Okay, but I don't really want to do that. In Haskell, for example, non-termination is not considered an effect, so it wouldn't be really quite a good match there. Okay, maybe. Yeah. Okay, other questions on this? I'll come back to it in a few minutes, but okay. So we want to write some programs. So I want to write some simple programs first. Oh, okay, maybe I should say we want to write some proofs, right? We know it's the same thing. Okay. So let's try to find a proof that A implies that B implies C, implies that A and B implies C. Anybody know what that's called, by the way, going from here to here? Actually, from here to here, it's uncurrying, right? You take a function that takes an argument, returns another function, takes a second argument, into a function which takes a pair of arguments at once, okay? So to get a proof of that, I can do two things. I can either use my two-dimensional notation, okay, or I can write a proof term. So let's write a proof term, okay? So what is a proof term for this? Okay, it has to be, well, it doesn't have to be, but morally it should be a function, right, which takes this as an argument and returns that, right? So it should be lambda f, let's see. Okay, so f is this type. Now what's the next thing? Okay, so it takes another argument, right? Because after I take lambda f, the right-hand side of the implication is another implication, which is another function. And so it takes, I'm going to call this p for pair, lambda p. Okay, so now f is this, and so this is, f has this type, and p has this type. Okay, so if you think about natural deduction, we worked bottom up for a while using two introduction rules, and we have two new assumptions, f labeled f and p. Now we want to construct a proof of C. How do we do that? Right, we take the function f, we apply to first of p, f applied to first of p, and then to the second of p. Okay? So these functions are actually easier to write than is to write the proofs, right? I don't know if you did that in exercise 1, but okay, very easy to write. What about the other direction? So if I say A and B implies C, I can get out A implies that B implies C. So that would be called currying. Okay? So can we write that proof? So it's an implication, so probably a lambda. Okay? Lambda G. Okay. Lambda G. Now the body of that, the right-hand side is going to be another implication, so we have a lambda. Yeah?
First P, close paren, open paren. What is that word?
Second.
Second, okay.
Okay. So here, the next thing we take x as an argument, right? Because we have another implication at the top. So because this function returns another function, so we have lambda x. What's the next argument? Well, the next thing is we take b as an argument, lambda y. Okay, now we have to construct a proof of C, which is the same as writing a term of type C. How do we write that term? We take G and apply it to the pair xy, right? So we take G and apply it to the pair x, y. Okay, so we have those two. Okay, so let's see what time it is. Okay, so you see that writing proofs is like writing terms, right? And writing terms is like writing proofs. Okay, so now let's try to do that over here with our monad examples. Okay. So hopefully all the rules can be up at the same time. Okay, so in a function programming language, there's two constructs to deal with monads, or two requirements for a monad to satisfy. Two types. What are they? Anybody remember? Or know that? Yeah? Return and bind. Okay. So return has type A arrow circle A, and bind circle A arrow A arrow circle B circle B. Okay, those are the two things. So now we should verify, right, that with our formulation there, we can actually realize these. We can prove these, right? So in other words, you can think of what Haskell does is it takes some kind of foundational thing like over this and gives it a presentation in terms of axioms, right? Where these are the axioms, these two, and these are sort of the proofs of the axioms that are in the background, okay? So let's try return. Okay, what's our proof of return? Well, the way we give a proof is we write a term, right? Okay, so we have to write a term of type A, well, circle A. Okay, how do we start? Lambda x. That's a good start. So x has type A. And now we have to create something of type circle A. What do we have available to create something of type circle A? Okay, we have to have, this is the introduction rule. So we put it in braces. And what do we put in braces? We have to put an expression E of type A lax, right? Okay. And the answer, somebody already gave the answer. What is that E that we're going to use? It's X. By the judgment by the lax rule up there, X is a term of type A, so X counts as evidence there. Okay, so there's no real computation going on. There's no let. Okay, no possibly effectful computation, because in this case, we actually have the value of type A, so we just deliver it, right? Okay. So that's our proof that A circle A. So the next thing is, how do we prove that circle A implies that A implies circle B implies circle B? Okay. So how do we start? Yep.
So what do the curly braces mean? It's not a test. I'm wondering what the curly braces mean.
Okay, so the curly braces mean so that the suspended computation will. Okay. A computation E which might have an effect, okay, encapsulated in the braces means don't run it now, because this is a term. It's suspended computation, okay. So this is a trivial suspended computation which will always terminate. Okay. So that's the way you should think about the braces. Yeah? Okay. Okay, so in order to prove this, how do we proceed? Well, we start with a lambda x, and x has type circle A, right? What's the next thing we take? An f, okay, and what's the type of f? It's A arrow circle B. Okay, now we have to create something to circle B. How do we do that? Braces. Okay. Okay. Just in case, I'm not sure if we have enough rooms, I'll put them down here. Okay, so put that into that place. Okay, so now we have to, what do we have to show in here? B lax, right? Because we got rid of the circle B, we went all the way to B. So now we have to show some computation that proves that B lax. And so how do we do that? Okay, we have to apply some elimination rule, right? We have broken down with the introduction rule everything, this implication, this circle. Now we're at B. We can't do anything with introductions, right? So now we have to apply some elimination. What do we have? Well, we have a circle A, and A implies circle B. Can we use the function f? Eventually, but not right away, because we don't have anything of type A yet, right? So how do we get something of type A? Right, we have to deconstruct x. We have to apply the elimination rule for circle A. So we say let brace x prime equals x in. So this x prime now has type A. Excellent. Okay, so now what do we do next? Okay, so we the f applied to x prime. What's the type of this? Circle B. What do we actually need here? No, because when we introduced the braces, we went through the circle, and we need something of type B, right? A computation of type B. So we have something of type circle B, where we need something of type B. How do we get that? Another let. So let y equals f of x prime in, what's the type of y?
Why do we have braces outside in the first place?
Okay, because we can't write let, because let, okay, is a computation which is C lax in, yeah, same problem as before. That's why we need the braces here. So the braces get us into the monad, then we compute, okay? And so here we just then return y, because y has type B, okay? And so this is a proof of this law over here, okay? Okay. Question?
Would this be the identity monad?
Identity monad? Well, it's a monad where the only operations you have are return and bind, no additional operations. So I don't know, is that called the identity monad? I don't know.
I think it's the simplest thing you can write down that has return and bind.
That's right, yeah. That's right.
The identity monad has another
Back, which we don't have.
Okay.
Okay.
So it's apparently not quite the identity monad.
Okay.
Yeah?
So I have a formulation with Jean is state of bind, which is going to two levels of circles. I was wondering, can we do that with this judgmental presentation with class? Because you can't do that person.
You want circle, circle A implies circle A? Okay, let's prove that.
This I
Hmm? We can define map. Okay. But yeah, so a circle, circle A implies A is a good example. If you compose effects, it's just as much as good as having just one effect, right? So you should be able to prove that circle, circle A implies circle A. Okay. How do we prove that? Well, we give a proof in terms of a proof term. How do we start? Okay. Lambda x. What's the type of x? Circle, circle A, right? So what do we do next? We need something of the circle A. How do we get that? Braces. So inside here we need something of which type? Inside we need something of type A. Okay, how do we get that? What do we have? Well, we can't do any introduction form anymore. We have to apply an elimination form. Right? How do we eliminate one of the circles here? Let x prime equals x. What's the type of x prime now? Circle A, right? Because we eliminate the outer circle. Okay, but we need something of type A. We aren't quite there yet. How do we get that? Another let x double prime equals x in. Okay, and now x double prime has type A, which is what we needed here. Thank you. Okay. Okay, makes sense? So that was a very good question, and we can prove that here. Okay. Okay. So we can prove all the consequences of the usual monad, sort of the things which should be true should be inhabited by using this kind of formulation. But there's something else that's usually in functional program that's important about monads. We don't just say that we have those two constructed, but we say something else. Right, we have some identities. Okay, so what are the identities? Anybody remember what they are? Yeah, the monad laws. What are they? Yeah?
Like return something, bind some function is f applied, that function applied to the argument. The same thing, but reversed.
Okay, let's see if you can
And then
write
it says
this down.
identity.
In terms of the return and bind over there. So you want to use bind okay, and we want to use Do we want to use return as this argument here? Is that?
Well, that one.
That's one of the laws, okay? Do you have another one in mind?
There's another word
Of A, or X, F equals F of X, equals return F of X. Or no, F of X, that's right.
F of X?
Yeah.
Okay, so let's look at that.
Does it make sense from the typing point of view? Let's just verify that, okay? So the first argument to bind should be of type circle A. So X should be of type A, right? So that this is circle A, which is okay as the first argument to bind. And the second argument of bind is type A arrow, arrow circle B, okay? And so it's okay to apply F to X because X is type A, and the result has type circle B. Did I do this right? Okay, so the types work out, and these two things should be equal. So when I reason about functional programs, I want to be able to use that identity. So now we should be able to check or refute whether in our formulation this is an equality that should hold, right? Okay. So hopefully I have enough on the board we can figure this out. Okay. So this was our return, right? And this was our bind. So if we write that out, what did we get? Okay, so bind is, okay, so maybe somebody can read it out to me because I can't. It's lambda x, lambda f, and then we have curly let x prime, right, equals x in y, okay, brace, close. So that's bind, and it's applied to a first argument, which is return of x. What is return? Lambda x dot brace of x. Maybe I should call this something else. How about z? And so then this is applied to z, right? That's the first argument, return applied to z. Okay, and what's the second argument? Well, that's just f. Okay, so let's see if you can calculate. So now we use our proof reductions, right, in order to see if we can simplify that. So this is substituted for the first argument x, and then this f is substituted for this bound variable f here. Okay. So if we do both of these substitutions, what do we get? We get let x prime equals, what is this x here? It's actually lambda x braces x applied to z in let braces y equals f of x prime in y. Okay, if I did this correctly, I substituted this f for this f that ends up here, substituted this term here for x in here and ended up in here. Okay, if I did something wrong, you should let me know. Okay. Okay, what can I reduce next? Actually, only one place where I can reduce at this point, right? This function. Okay. So if I rewrite that, it's let x prime equals braces z in let y equals f applied to x prime in y. Okay, what happens next? Anybody see? The first let, I have a brace matching a brace, right? So I can substitute z for x prime, right? Okay. So I get the let goes away. And this is the easy case of the substitution because this is just the term z. So I don't have to worry about whether it happens on the left first or on the right. So I get let braces y equals f of z in y, right? Just substituting z here, here. Okay, now this is what I want. What do I want as a result? F of z. What do I have? This. Right. Where's our eta rule? Here. Wait, where is it? Here. Okay. By eta, these two, a term m is equal to let braces x equals m in x in braces. Right. That was our eta rule. And magically, okay, that's f of z. Okay. So indeed, this monad laws hold, okay? This particular one. And so there's two more to check, right? Yeah?
Yeah. Is that definitional equivalence?
So, okay. Up to it's just reduction. And reduction induces definitional equivalence, right? Because it's from computational reductions, okay? This thing here is certainly inequality, but the question whether it's definitional is something that Bob will have to answer. Right, because these rules are all beta, and this is an eta rule. So the question is if you're willing to accept eta rules in your computation. When we reason about Haskell programs, we would be willing to accept this kind of an eta rule. But if we build a full type theory, there's other considerations, so we might not want that rule there. Okay, but it's a very good point. So in these kind of calculations, okay, we do need eta rule here. Okay. Other questions? Okay. So let me not try to verify another one. Maybe this will be one of the assignments. You can verify the other two monad laws. Okay. But let me just try to back up one step and let me try to summarize what we have done. Okay. So we already started in the last time the computational interpretation of proofs. And the way we did that is we annotated our judgments with proof terms. Okay. And the proof term was just another way to write down the proof. So what we do here, if you want, you think of these as programs, right? But we're really calculating with proofs. Except if we really try to do this with a proof, right, we'd be here for a long time. Because we'd have these big two-dimensional figures. We have to write another big two-dimensional figure, right? It was bad enough to write it down in these terms. Okay. And the notion of computation arose from proof reduction. And proof reduction arose from an introduction rule followed by an elimination rule. And at the end, it kind of, all the way down, it becomes substitution. So the computational engine at the lower level of judgment is just substitution. Okay, so now we wanted to capture this idea that there's something weaker than truth, okay, which is a generic idea of a computational effect, like it might not terminate, okay, or it might terminate, but it might have some other effect along the way. And for that, we introduced the judgment A is lax, and E is a computation of A lax, which means that it may or may not deliver A, or if it delivers A, maybe up to some effect. Okay. Okay, and then we wrote down what has to hold for this judgment. Okay. So lax is weaker than truth. So certainly if A is true, then A is lax. But the interesting part of it is when you have a computation which maybe delivers an A, if we're allowed to assume that it delivers one, as long as we only prove that we have something that's a computation and only conclude that it's a computation possibly having an effect. And that actually is a substitution principle, which is a defined operation, which, if you look at it carefully, okay, actually sort of sequences the computation so that whatever idea you had about the way the effects of sequence is actually reflected in the notion of substitution. And then we internalize the judgment of A is lax, okay, as a proposition, circle A true, and wrote down introduction elimination rules for it. Okay. And these introduction elimination rules allowed us to write ordinary terms, okay, in which some expressions are embedded that actually do computation. And then we went through and said, okay, if you want to present this as a theory in a programming language, it should be presented not as an extension, if you can, with this new notion of expression, but maybe axiomatically by giving some things that have to be there. Okay? So in Haskell, they're presented this way at the language of terms. And then we verified that, yes, with our notion of lax truth, or circle A, we can actually give a generic implementation of these. Okay? And in fact, these are then provable under this interpretation. And in fact, we can verify that the monad laws, which are used to reason about functional programs written with monads, actually are proof equalities based on the proof theory that we developed before. Okay. There is a sort of another direction that you might want to take. You might want to say that whatever you can do with monads in a functional language, you can also do here. Okay. And in some sense, you want to be able to go back and forth between the two. And so there's a paper I wrote about 10 years ago or so where you can read how you can actually show that things work in both directions if you want. And then the way this is used in a functional language, of course, is not just with this very generic monad, but you have additional operations for different types of monads. There's not just one circle, but there's different monadic sort of constructors that satisfy these laws for different kinds of effects, like exceptions, like store effects. And the identity monad, as I heard, is one, okay, where you can get from circle A out back to A. Okay. Questions about this? Okay, so I didn't get around to talking about Freude-Nivelle. I think it was worth doing this in detail because, I mean, it's not, when you have an idea about to capture something, it's not a trivial thing. There's always sort of a hard road to understand these things and make sure that one has a proper foundation for what one is trying to do. But in the end, it turns out monads are just logic. Okay, that's what the lessons is. And the computation rules of the generic monad just correspond to proof reductions, just like we did before for generic functional programming. Okay. And the conceptual leap we needed to make in order to make this work is to say there's more judgment than just truth. There's also this idea of possible truth or lax truth, which is somewhat weaker, because we're not guaranteed to actually have a proof of A. We may or may not have a proof of A, and we have to account for that in our rules. Okay. More questions? Okay, then I finished exactly on time. Okay.